The modern internet runs on light moving through glass. But the next internet may need something much more delicate. Quantum networks do not just send ordinary bits. They try to move qubits and entanglement across real-world distances. That is powerful because entangled particles can stay deeply connected, even when they are far apart. The problem is that classical fiber, while amazing for today's web, is not perfect for fragile quantum states. As photons travel through glass, some are absorbed, scattered, or distorted. That slowly damages the information they carry. For normal internet traffic, engineers can boost and resend the signal. For quantum data, that simple trick does not work. A classical repeater measures a signal, cleans it up, and sends a fresh copy onward. But measuring an unknown quantum state changes it. In many cases, that destroys the original information. This is tied to a core rule of quantum physics. You cannot simply copy an arbitrary qubit the way you copy a classical file. That is why researchers are developing quantum repeaters instead of ordinary network boosters. These devices aim to extend entanglement link by link using techniques like entanglement, swapping, and purification. Another crucial piece is quantum memory, a system that can briefly store fragile states until the network is ready. Some labs use cold atoms. Others explore crystal defects, trapped ions, or specialized photonic devices. Each approach has trade-offs in speed, stability, temperature, and cost. Researchers are also testing better transmission media, including hollow core fiber that reduces how much light interacts with glass. In those designs, more of the light travels through the empty center, which can reduce some losses and delay. Better sources and detectors matter too. A quantum network is only as good as its weakest photon. Right now, many experiments work over lab benches, campuses, or city-scale links. Global scale is still a major challenge. One solution may come from space. Satellites can connect distant points without forcing every photon through thousands of kilometers of fiber. Countries across the world are racing to build early quantum communication networks for science, security, and national infrastructure. One of the first major uses is highly secure key distribution, designed to reveal when a link is being observed or intercepted. Later on, these links could connect distant quantum processors and make them work together as one larger system. This does not mean today's fiber becomes useless overnight. It means tomorrow's infrastructure will likely be hybrid. Data centers, telecom routes, and research labs may add quantum hardware gradually rather than replacing everything at once. The real challenge is architectural. How do you build a network that supports both classical traffic and fragile quantum links? The answer will likely combine improved fiber, quantum repeaters, memory buffers, error reduction, and smart routing. For telecom companies, this is not just a physics story. It is a long-term infrastructure decision. The winners may be the networks that prepare early for secure communications, precision timing, and distributed computing. So are fiber optics obsolete? Not exactly. But for the quantum era, the old playbook is no longer enough. The future internet will not depend on faster glass alone. It will depend on entirely new ways of storing, protecting, and sharing light.